You know that little box on your phone charger? Ever wonder what's actually inside it? Well, there's a piece of 19th century tech in there that's pretty much the unsung hero of our entire modern world. We are just surrounded by electricity, right? But the journey it takes to get to us is honestly fascinating. So today we're going to pull back the curtain on the incredible and usually invisible device that makes it all possible, the transformer.
So let me ask you this. How does electricity actually get from a power plant, which could be hundreds of miles away, all the way to the plug in your wall? On the surface, it sounds simple, right? Power plant, power lines, your house. But getting that electricity across those huge distances is a massive challenge. It's a fundamental physics problem that almost stopped our modern power grid before it even got off the ground. Okay, so here's the big problem. Think of it like a really long garden hose. The longer that hose is, the more water is going to leak out before it ever gets to the sprinkler, right? Well, it's kind of the same with electricity. That leak is energy just escaping as heat from the power lines. It's a huge deal. Without some kind of solution, most of the power being generated would literally just vanish into thin air before it could ever power your TV.
All right, let's dive into the problem with our power grid. I mean, this was the central question during the whole war of the currents back in the late 1800s. You had Edison, who was all about direct current, or DC, but the problem was it just couldn't travel very far. And then you had Tesla and Westinghouse, who were pushing for alternating current, or AC. That's where the electricity is constantly flipping direction. And they had a secret weapon, something that could solve this whole distance problem.
Okay, so here's the brilliant part. The amount of energy that's lost as heat, it's not just related to the current, it's tied to the current squared. What does that mean? Well, if you can cut the current in half, you don't just cut the power loss in half. No, you reduce it by a factor of 4. It's a huge difference. And basic physics tells us there's a trade-off. For the same amount of power, if you crank the voltage way up, the current has to go way down. So the solution is obvious, right? Just send the power over the lines at super high voltages. But how on earth do you change the voltage?
And this is where our hero finally enters the story. Meet the transformer. This was the absolute game changer, the winning move for AC power. It's just such an elegant solution. A device so ingenious that its basic design has stayed pretty much the same for over 100 years, just quietly working in the background as the linchpin of, well, everything.
So what exactly is it? A transformer is a simple, static, and that's a really important word, electromagnetic passive electrical device that converts electrical energy from one voltage value to another. For me, the most amazing word there is static. That's the key. A transformer has 0 moving parts, no gears, no spinning motors, absolutely nothing to wear out. It's just a solid, silent block of metal and wire that does this incredible job using nothing but the fundamental forces of nature.
So what does a transformer actually do? Well, you can think of it like a gearbox for electricity. It can step voltage up or step it down. And when it does that, the current does the opposite. But here's what it doesn't do. It doesn't change the frequency of the power, and it definitely doesn't create any new power out of thin air. It's just a converter. It links 2 different circuits together using only magnetism. Pretty wild, right?
So, let's talk about the magic of induction and how this thing actually works. Because linking 2 circuits with just magnetism, I mean, that sounds a little bit like magic, doesn't it? But it's not. It's pure physics, based on a principle called electromagnetic induction. Let's break down how it all happens. All right, the secret sauce here is something called mutual induction. Here's how it works. When you send an alternating current, remember that's the one that's always changing direction, through a coil of wire, it creates this pulsing, constantly changing magnetic field all around it. Now get this. If you put a second coil of wire close by, not even touching the first one, that pulsing magnetic field will magically create a brand new electrical current in the second coil. It's like energy is jumping across an invisible gap.
Okay, let's walk through the 4 steps of transformation. Step 1, AC current flows into what we call the primary coil. Step 2, because that current is alternating, it creates a constantly changing magnetic field. Then, step 3, a soft iron core acts like a highway, guiding that magnetic field exactly where it needs to go. And finally, step 4, that moving magnetic field passes through the secondary coil and induces a totally new AC voltage on the other side. That's it.
And I just love this quote. The 2 coil windings are not electrically connected, but are only linked magnetically. I mean, that's the whole mind-blowing part, right? The 2 wires are completely separate. The input circuit and the output circuit never touch. All that power is being carried across the gap by nothing more than an invisible magnetic field. It's such a clever and incredibly robust,
design.
So that brings up a good question. How does the transformer know how much to change the voltage? It seems like it would be really complex, right? But the answer is, well, it's actually shockingly simple. It's all about ratios.
Let's compare step-up versus step-down transformers. The secret is literally just counting the number of times the wire is wrapped around the core on each side. It's that simple. If you want to increase the voltage, that's a step-up transformer, you just need more turns of wire on the output coil than the input coil. And if you want to decrease the voltage, a step-down transformer, you guessed it, you have fewer turns on the output coil. More turns, more volts. Fewer turns, fewer volts. That's the rule.
Okay, let's look at a quick example. Imagine we have a transformer with a turns ratio of 3:1. All that means is that for every 3 wraps of wire on the primary side, the input, there's only 1 single wrap of wire on the secondary side, the output.
All right, pop quiz. Knowing what we now know, let's put it to the test. If we apply 240 volts to the primary winding of this 3:1 step-down transformer, what do you think the secondary voltage is going to be? Think about it for a sec.
80 volts. That's right. You just divide 240 by 3. The voltage changes by the exact same ratio as the turns of wire. It's just a beautifully simple and totally predictable relationship.
All right, now let's talk about why all this matters: power, loss, and efficiency. We have all the pieces of the puzzle now, so let's connect it all back to that original problem and see exactly how this amazing device makes our whole power grid work.
Okay, check out the power of stepping up voltage. This is why transformers are so absolutely critical. At the power plant, they use a massive step-up transformer. Let's say it increases the voltage by a factor of 10. Well, that means the current decreases by a factor of 10. But remember that rule about power loss being the current squared? That means the energy lost as heat gets reduced by a factor of 100. That is a massive, massive energy saving.
And what about the transformer itself? Is it wasting a lot of energy? Nope. A real transformer's efficiency is incredible. We're talking like 96%, sometimes even higher. Because there are no moving parts, hardly any energy gets wasted, just a tiny bit of heat loss in the copper and iron. Honestly, they're one of the most efficient large-scale machines that we've ever built.
So think about it. This simple 19th century device is what powers our entire digital world. From the giant transformers you see at a power station all the way down to that little box charging your phone right now. This humble, silent device is efficiently managing the flow of energy that makes modern life possible. It kind of makes you wonder, right? What other invisible inventions like this are hiding in plain sight?